we're asked to sketch the graph of this function alongside its parent function. And they're not being explicit with what the parent function is, but the parent function, we can call it g of x. That'd be like the original function before you start messing with it. And we're going to assume it's this log base 3 of x, because the plus 2 part is like the alteration of the function. So this would be the parent function. The function of x before we did a vertical or a horizontal shift, before we did this part. That's the parent. That's the original function. So to sketch a graph of these two, what you probably want to do is pick some particular points, because a graph of any type of logarithm, it looks something like this. Okay? Its growth does slow, but it actually never stops going up. There is no upper limit to the range. The range for these logarithms is going to be the same as the range of any type of logarithm without any funny business going on. It's negative infinity. That's the lowest y value you can have. Positive infinity, that's the highest y value you can have. Okay, now the domain we'll check out in a little more detail, but the domain for my graph here, 0 is the smallest value I can get in the x-axis, but I use a parentheses because I never actually can reach 0. I can't plug in 0. And then positive infinity would be the highest x value I can have in this graph because it keeps going to. Okay, but let's do it specifically for this problem. Okay, let's do the parent function first. Let's make a quick data table. The base of 3 is important. That's saying, like a logarithm says, what power do you need to raise 3 to be to make it equal your x in here? Okay, so we can plug in some numbers for x, and you probably want to start with this case. Look, if you do log base 3 of 3 in like an online calculator, it's going to give you 1, because you raised 3 to the power of 1 to make it equal to 3. So that's the y value that comes out for our parent function. Let me color code this. Parent function is blue, so I'll do this in blue. Okay. We plugged in 3, we got out 1. Now let's think of other powers of 3 to plug in. You could plug in some other numbers, but it's going to get kind of tough to look at because they're going to be decimal numbers. Look, we got 3 squared would make 9. So if we plug in 9 in for x, that'd probably be a good one to do. And again, look for, you could Google search a calculator, a log base 3 calculator, and it'll come up with something where you can change the base. But what this is saying is if I'm plugging in 9 in for x, it's the value that comes out of the logarithm is the power you raise 3 to be to make it equal 9. So what power do we put on top of the 3? What power do we put here to make it equal 9? Right? So 3 squared would make 9. It's a 2. So that's all a logarithm is. It's that power that you raise the base to make it equal to inside the parentheses. We can do another one. 3 to the third would be 27. So 27 is another good one to plug in. Log base 3 of 27. That says, what power do you raise 3 to make it equal 27? The answer is 3. 3 to the third makes 27, right? So that's our graph. Actually, let's sketch that. The colors that they want. Here's the x and y axis. I need to go 3 on the x-axis, and I should have 1 on the y-axis and put a dot for my parent function. I should go to 9 on the x-axis. I'm not sure how far the computer goes. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 on the x-axis, 2 on the y-axis, and put a dot. And then actually one other good value to plug in would be if you plug in 1 in for x. I'll show you why. Because if we plug 1 into the parent function, in for x, so I just replaced x with 1, the question says, what power do you raise 3 to make it equal to 1? And we actually have a special power for that. Any power, anything to the 0 power equals 1. So 3 to the 0 power would equal 1. So 0 is the result of that logarithm. So that's a nice easy point. 1 in the x, 0 in the y. It's going to make that classic logarithm shape through those points that we discussed at the beginning. Okay, so there's the parent function. Sorry for the delay. Get rid of all this. And let's get red out. So let's graph f of x. Make an x and y table to get some specific points. If I plug in 0 in for x, let's see what f of x gives us. That's log base 3 of 0 plus 2. So we need to figure out, wait, why did I pick 0? That's not a good one, because what power do you raise 3 to be? What power do you put here to make it equal to 0? Right? That's what this logarithm part says right here. What power do you raise 3 to be to make it equal to 0? And you can't. It's infinite. You know, you approach negative infinity to make that happen. So that's not an actual value on the graph. Let's try out x equals 1, though. That's something we can get. If I plug in 1 into f of x, just put 1 where x is. What power do you raise 3 to be to make it equal to 1? That's what we discussed before. 3 to the 0 would equal 1, right? So this result is 0. That is defined. And then 0 plus 2 makes 2. Again, you could do this with a calculator. You don't have to do it by hand like I'm doing. Log base 3 of 1 equals 0. And then more powers of 3. Let's plug in x equals 3 again like we did. And if you do that, log base 3 of 3, that says what power do you raise 3 to be to make it equal to 3? Well, it's just 3 to the first power makes 3, right? So 1 is the result there. 3 to the first power equals 3. So the power that we need is 1. And 1 plus 2 makes 3. So you can see probably the pattern. We go 1 in the x, 2 in the y. Everything is just, every point that you see down here has been bumped up 2. So this is at 3, 1. Now it's going to be 3, 3 for f of x because it's been bumped up 2 y coordinates. And then if we're at 9 on the x, the parent function was at 2 on the y. 9 on the x, we should be at 4 on the y because of our vertical shift of plus 2. So that is a graph of f of x. Those are the two graphs that we should be looking for. Okay, and so this part over here, they want the domain, the range, and the asymptote. The domain are all the possible x values you can plug in. And we saw in, let's see, I think I might have cut out the instructions, but I think they want it for f of x. I don't see why they'd want it for the parent function. But the domain for the parent function is 0 to infinity because the smallest x value we can have approaches but doesn't actually touch 0. So that's why we use a parentheses 0. Okay, don't use a bracket 0 because you can't have exactly 0. We just saw you can't plug in 0 and get out a value. But pos infinity, because you can plug in whatever number you want in for x, your calculator will give you something for y, as long as it's not negative. So that's the domain, all the x values. The range are all the y values. Look at these graphs. They keep going down, right? So negative infinity is the lowest value we can have for the y values. And they do keep going up. They might slow down, but they never stop increasing. So pos infinity is the range. And the asymptote, I think they want specifically the vertical asymptote. That happens right here at x equals 0 for both the parent and the shifted function. Because you never reach x equals 0. You get really close to 0, we said, but you can never actually get out 0 for a y value. That can't happen.